Okay, so today we'll try to cover non-convex optimization and also a little bit of minimax optimization, in particular convex concave minimax optimization, also called as saddle point optimization. Okay, so let's start with non-convex optimization. So
can I ask you a quick question from yesterday? This Praneeth. Oh, yes, so basically, yeah, you mentioned that there is some connection with importance sampling and then essentially how you choose the weights, etc. Can you send us some reference on that?
Sure. Actually, my notes have some of that. So,
okay.
So, so we are scanning all the notes and we'll put them on the website.
Oh, very good. Thank you so much. Thank you.
I can point you to the precise location.
Thank you. Thank you so much.
So the general problem is that we want to minimize again a function f of x, but we are now not guaranteed that the function is convex. And in general, this is a computationally hard problem, and we cannot do. And there are very simple lower bounds which show that we cannot minimize such a function under like 0th order or first order or any kind of oracle with number of queries which is less than exponential in the dimension. Okay. Okay. So what do we then do? So the first thing that people started asking is we can still run gradient descent on these kind of problems. And what can we say about gradient descent when we run on these non-convex functions? Okay. And one of the maybe even folklore kind of results is the following, that if f is L smooth, there is no convexity assumption here. And we run GD. Eta less than or equal to say 1 over L. Okay. Or let's say we choose eta to be equal to 1 over L. Then what we have is that 1 over T summation T equal to 0 to T minus 1. Norm grad f of xt square is less than or equal to 2L times f of x0 minus f of x star divided by t. Okay. So what this says is that if you look at the average norm of the gradient over all the t iterations, then it goes down as 1 over t. Norm square of the gradient, then it goes down as 1 over t. And the proof of this is fairly simple. So we can just quickly do it. So again, recall that gradient descent is just xt plus 1 is xt minus eta grad f of xt. So f of xt plus 1 using the smoothness condition is less than or equal to f of xt plus grad f of xt times xt plus 1 minus xt, which is minus eta grad f of xt. Plus L over 2 eta grad f of xt square. And this is nothing but equal to f of xt minus, so we substitute eta equal to 1 over L. So we'll get 1 over 2L. Okay. Now we take a telescopic sum and average. So because gradient descent is reaching these kind of points, intuitively what this says is that if I just look at the first order variation around the point, then it's kind of flat. in terms of first order variation. So gradient descent is reaching those kind of points, and after t iterations, it can find those points for which the gradients are quite small, right? And these points are called first order stationary points. So a point is called epsilon first order stationary point if norm grad f of x is less than or equal to epsilon. Okay. So what this says is that if you gradient descent can find first order stationary points, in particular epsilon first order station 1 over square root t first order stationary points after t iterations. Okay, that's what gradient descent shows. Now let's go to the slides. Slideshow. Okay. Okay. So as I mentioned, so we are looking at this non-convex optimization problem where we want to minimize over x, f of x, and gradient descent, as we just saw, xt plus 1 is xt minus theta grad f of xt. And the first question we would like to ask is how it performs. And again, we saw here that it actually converges to first order stationary points. And more quantitatively, a epsilon first order stationary point is that for which the norm of the gradient is less than or equal to epsilon. And what we showed here is essentially that gradient descent can find epsilon first order stationary points in 1 over epsilon square iterations. Okay. Now, we would like to understand, are these first order stationary points good enough, or how do they look like in general non-convex optimization problems? And in general, there could be 3 different kinds of first order stationary points. One kind of points are maybe local minima, right? The other kind of, so here again, the gradient is 0 at a local minimum. Similarly, even at a local maximum, the gradient is equal to 0. So even local maxima are first order stationary points. And finally, there could also be saddle points where the point is minimum in some directions, but then could be maximum in some other directions, right? And first order stationary points could be any of these. And how do we distinguish these different cases? So one way we could try to distinguish is that we look at the Hessian. So if the Hessian is positive semi-definite, then it means that it's actually, it could be, so for local minima, Hessian is positive semi-definite, meaning that the gradient is, the second derivative is always a positive semi-definite matrix. And for local maxima, the Hessian is always a negative semi-definite matrix. And for saddle points, in general, Hessian could be just indefinite. It could have both positive as well as negative eigenvalues. Okay. But because we are looking at a minimization problem, we are more interested in finding these kind of at least local minima problems, local minima, and not local maxima or saddle points. Okay. And one way to distinguish first order stationary points as to whether they're local minima, maxima, saddle points is to try to look at these second order derivative and see whether the Hessian is also positive. So if a point has both first derivative equal to 0 and second derivative being a positive semi-definite matrix, it's called a second order stationary point. Okay. So first order stationary point only looks at the gradient, says that gradient is equal to 0. Second order stationary point says that the gradient is equal to 0 and the Hessian is also a positive semi-definite matrix at this point. Okay. And it turns out that in many problems that have been studied in machine learning, it turns out that even though they are non-convex problems, second order stationary points seem to be good enough in many problems, in particular in matrix factorization related problems, where if you find any second order stationary point, then it turns out that it's almost as good as a global minimum. Okay. In some cases, there are approximation guarantees, and in some cases, people have shown that they're exactly the global optima. And this is not a general result, but is specific to certain problems that people have considered, and heavily uses like the statistical nature of the problem from which it arises. Okay. So,
Praneeth, so you're saying even though the local minima and global minima might be like the actual cost might be very different.
No, I'm saying here they may be quite similar. So even though it's non-convex,
yeah,
the kind of symmetries in the problem are such that any local minima is also a global minimum. or close to being a global minimum.
The nature of the cost function is like
Nature of the cost function is like that, and these are some examples of cost functions where it turns out to be like that.
Okay.
Yeah. So the point is, this motivates that you might at least design algorithm which can find second order stationary points, because at least in these kind of problems which are non-convex, it can still give you good results. Right?
So symmetries of the problem meaning symmetries of
so sometimes there are some permutation invariances. So if X is a solution, then any permutation of X might also be a solution. So it's necessarily non-convex because if X is a minimizer, then any permutation of X is also a minimizer, but anything in the middle may not be a minimizer. So it necessarily has like multiple minima, but then any local minima is still as good as a global minima.
Because they're all connected by that symmetry.
Yeah. They're not connected in like a
Not in that sense.
So for example, in low rank matrix factorization, if you are parameterizing the problem as U times V transpose, you can put any rotation matrix R transpose in the middle, right? So UR and RV VR are also valid solutions. So this naturally motivates the question of how to find second order stationary points, and more quantitatively, second order stationary points can be defined in this way. So the first one, the norm of gradient less than or equal to epsilon, is just the first order stationarity condition. The second one, we want that the Hessian is positive semi-definite. In this case, because we are looking at approximate, we want it to be almost positive semi-definite. So we would require that the minimum eigenvalue of the Hessian is at least minus square root of epsilon. Okay. This epsilon and square root epsilon are maybe not super important. We can replace it with epsilon 1, epsilon 2, and so on. But it turns out that this somehow equalizes the difficulty of both the aspects. Okay. So there is a famous method called cubic regularized Newton's method, which can find these kind of points. This we briefly mentioned in one of the earlier lectures, where we were looking at functions which have Lipschitz continuous Hessians and what's the natural notion of gradient descent for these kind of problems when you have Hessian information and so on. So it turns out that this method, cubic regularized Newton's method, it is exactly the equivalent of gradient descent when you also have Hessian information, and it can indeed find these second order stationary points. However, as I mentioned, like this does require Hessian information, and we have also discussed that second order information, meaning the second order oracle, is significant, strictly more difficult to implement compared to the first order oracle. So gradients can be computed in pretty much the same time as the time taken for computing the function value, but the same is not true of the second derivative, the Hessian. Okay. Yeah. So it turns out that there is a simple modification to gradient descent, which is about adding perturbations. And people have shown that it can also find epsilon second order stationary points in these many number of iterations, poly of D over epsilon, where D is the dimension of the problem and epsilon is the desired accuracy. Okay. But if you recall, most like all the results that we have seen so far have depended on problem specific parameters like smoothness, strong convexity, and so on, but they did not have any explicit dependence on the dimension in terms of convergence rate. So the convergence rates were always 1 over epsilon, 1 over epsilon square, 1 over square root epsilon. There was no dimension dependence. And here there is a polynomial dependence on the dimension. So the first question we ask is whether perturbed gradient descent can converge to second order stationary points efficiently, meaning that can we get dimension independent bounds, just like we had these gradient descent and accelerated gradient descent kind of convergence rates. Okay. And it turns out that the answer is yes, and we are able to get a bound which is not completely independent of the dimension, but improves this polynomial dependence to a polylogarithmic. And there have been subsequent papers which actually show that at least a log dependence here is unavoidable information theoretically. Okay. So at least for this non-convex setting for finding second order stationary point, there is a lower bound which is not maybe polylog of D, but log of D divided by epsilon square.
So what is the difference between O and O tilde? O
twiddle has some additional log factors involving these quantities. So it will have poly log of this entire, so poly log D and poly log of 1 over epsilon square.
Okay.
Polylog means
log d to the some constant power. That's polylog d. And O twiddle hides logarithmic factor in this entire whatever is you are seeing here. So that will be polylog log and polylog of 1 over epsilon. Okay. So this is for gradient descent, and as they have seen, even in the standard smooth convex minimization setting, gradient descent is not in fact the optimal algorithm when we have smoothness. And Nesterov's accelerated gradient actually converges faster than gradient descent for the smooth convex optimization problem. And in practice, actually, there have been some influential papers which have observed that accelerated gradient descent can be much faster than gradient descent even for like highly non-convex problems, including the training of neural networks. So this acceleration idea is quite widely used in many non-convex optimization settings, including in the training of deep neural networks and so on. Okay. However, like the best result we had known in theory earlier was only about first order stationary point convergence in 1 over epsilon square iterations for accelerated gradient descent. And this would suggest that there is actually no improvement over GD, right? So the second result that I want to mention now is.
So is it the same acceleration that you did when you showed for convex case?
That's correct. Yeah. So I'll come to the precise algorithm. So there is maybe some slight modifications, but the intuition is exactly the same.
So for convex functions, this was exponential, right? The convergence?
Convergence was exponential if you have also strong convexity.
Strong convexity.
If you don't have strong convexity, the function could be flat in some regions. Then we had 1 over square root of epsilon, which corresponds to 1 over t square. Yeah. Yeah. So already from convex to non-convex, the rates themselves don't really mean much, because in convex optimization, we are looking at function values of optimality, right? Here we are looking at the norm of the gradient, right? So the measures that we are using to measure optimality itself is different. That's because in convex optimization, function suboptimality is something tractable that we can minimize. Here we cannot really minimize functions of optimality, because in general, global optimization is computationally intractable, right? So we have a weaker notion which is called this first order stationary point. So in this notion, we are getting 1 over epsilon square iterations. Okay. So the second result that I would like to describe today is that so we can actually design a pretty like essentially analyze the same accelerated gradient descent algorithm that we analyze for the smooth convex optimization setting, and then show that it can find second order stationary point in polylog d over epsilon to the 1.75 steps compared to polylog d over epsilon square that we can show for perturbed gradient descent. Okay. So yeah. So the main two ingredients of this result for accelerated gradient descent are a perturbation step, and then what is called a negative curvature exploitation on top of this accelerated gradient descent. And so there was this very nice paper by Karman et al., which actually introduced this negative curvature exploitation. And I'll explain this step in more detail when we get to the more precise description of the algorithm. Okay, so let me just quickly summarize the results that I would like to speak about, and then we'll go into the more details about how we show these results and so on. Okay, so the first, the summary is that convergence to second order stationary points is important, at least in several applications in practice, and pure gradient descent and accelerated gradient descent can indeed get stuck near first order stationary points because there is no gradient information to move around. But if you add a little bit of perturbation, we can see that perturbed gradient descent can actually find second order stationary points in polylog d over epsilon square number of iterations, where epsilon is the quantification of the first order stationarity. And similarly, there is this perturbed accelerated gradient descent plus this negative curvature exploitation, which can find second order stationary points in slightly better time, which is polylog d divided by epsilon to the 1.75. Okay. And there are many more works, further works in this direction, which extend these results to stochastic settings where we only have access to stochastic gradients and not deterministic, like full gradients and so on. So in the rest of this talk, let me try to present the main ideas of the proof of this result as well as this result. So any question about anything so far? Okay.
So just one question for the
Yeah.
Hessian. Why are you taking care of it in the square root scale?
Yeah. So I mean, the general result, you can put an epsilon1 here, and then you can put an epsilon2 here.
Okay.
And then you can get a bound which is in terms of epsilon1 and epsilon2. But
Okay.
like when you try to match the dependence on epsilon1 and epsilon2, it turns out that this is the right scaling.
Okay. That's the optimal thing to do.
This is the optimal. Otherwise, like you'll get something like 1 over epsilon1 square plus 1 over epsilon2 to the 4.
Okay.
Right? Something.
You're balancing that trade-off there. Thank you.
Yeah. Okay. So let's now go over like the main ideas of the proof of gradient descent. So these are the assumptions that we'll be making about the function. So the function is gradient Lipschitz, meaning that the gradient, so the norm of the difference between the gradients at x and y is less than or equal to a constant times the norm between x and y. Yeah.
I just trying to understand. Now see this. Now this in this problem, basically f of x can have multiple minimas, right?
That's correct.
And all the minimas are more or less equivalent.
That's correct,
right?
Yeah.
So you are happy with basically finding any of them.
Any of them.
Right? And then like this, even the previous argument, which is this just gradient descent.
Can you please use the microphone? Sorry, I can't hear the question.
No, and the question is basically this f of x can have now multiple minimas.
Yeah.
And all the minimas are more or less equivalent, basically, right? So, and you are happy with finding
yeah.
any one of them. So, if you use the like method for finding this minima for the convex optimization problem,
yeah.
If you just use it straightforwardly, that should work here, right? Because it will just probably find the closest minimum, no?
So it can okay. So it can get stuck in a saddle. So let's say you start at a saddle point.
Okay.
Then gradient descent will not move from there.
Because
there is no gradient.
There's
gradient
no
is equal to 0.
Okay.
Right.
Okay.
So now there have been some arguments which say that if you do a random initialization, then it will probably not start at saddle points because saddle points are a measure 0 set among like all the data points. So if you do a random initialization, it will not start there. But there have been also results which show that even with random initialization, it might take you exponential amount of time to escape saddle points.
But suppose if you just do gradient descent and find whatever the stationary point.
Yeah.
And around this stationary point, if you just again do some kind of stochastic movement.
So that's precisely what this perturbed gradient descent is trying to do.
This is what this is.
That's what this is trying to do. So you do gradient descent always.
Okay.
And whenever you see that your gradients are very small, you add some amount of perturbation, then you do gradient descent.
Okay.
That's precisely the algorithm. And so we'll show that it can actually escape these saddle points efficiently.
Okay.
Meaning that it will find second order stationary points in this amount of time.
Okay.
So that's precisely the algorithm.
Okay.
Yeah. Okay, so what do we assume about the function? So we just assume these three conditions. So the first one is gradient Lipschitzness, that the norm of the difference between gradients at x and y is less than or equal to the norm of x minus y. Okay. The second one is the Hessian Lipschitz condition, and this is required because we are talking about second order stationarity, meaning that Hessians should be well defined. And if Hessians are not continuous, then at some point the Hessian might be actually second order, like positive semi-definite, and then you move just a little bit, it might no longer be positive semi-definite. So you need some kind of stability for the Hessian in order to talk about second order stationarity. So the second assumption that we make here is that instead of Hessian Lipschitzness, that the operator norm, or like the largest singular value of the difference between Hessian at x minus Hessian at y is at most the norm of x minus y. Okay. So there are some constants here, so that's why I did not put exactly less than or equal to, but I'm assuming that like these are some constants. And for simplicity, I'll not show the dependence on those constants, but like all of that can be tracked very precisely. Okay. So the third assumption is that the function is lower bounded. And I mean, this is not really an assumption in the sense that we can, even without this assumption, we'll be able to say that either we'll find a second order stationary point or we'll keep on decreasing the function value and so on, right? So if the function value goes to minus infinity, then we can just keep going and we'll probably not find any second order stationary point, right? Because the function just keeps on decreasing and we'll just keep on moving. So this assumption is just to ensure that second order stationary points even exist, right? For linear function, for example, there is no second order stationary point. You can just go to minus infinity. Okay. So these are the only 3 assumptions. And the question is, how does gradient descent behave under these conditions, right? So we look at the gradient descent step. So xt plus 1 is xt minus eta times the gradient f of xt. And there are 2 possibilities. One is when the norm of the gradient is large. The other one is when the norm of the gradient is small, right? So when the norm of the gradient is large, we know that the function value decreases by at least this much. And that's precisely this inequality here, right? Because of smoothness. Okay. And in this case, we are happy because the function value decreases significantly. And because the function is lower bounded, this can happen only so many times. It cannot just keep happening repeatedly, right? Now, the other case is when the norm of gradient is small. In this case, there are 2 possibilities. One is that we are either at a second order stationary point or we are at a saddle point, right? But we don't know which one it is because we are only looking at the gradients. And in both the points, gradients are equal to 0. And we don't know the Hessian, so we a priori don't know how to distinguish between whether we're at a saddle point or second order stationary point. So the question is, how do we escape the saddle points if we are at a saddle point, right? And the algorithm that we want to do is precisely the one that we just discussed, which is perturbed gradient descent. So for t equal to 0, 1, and so on. So for every iteration, we check for some perturbation condition. If it holds, we add some small random perturbation. Okay. Otherwise, we are just doing gradient descent. Okay. So the algorithm is extremely simple. So we pretty much just keep doing gradient descent, and every iteration we check for some perturbation condition. If it holds, we add some random noise, which is sampled uniformly at random from some ball of radius epsilon, and we again keep doing gradient descent. Okay. So the first thing to note is that between 2 perturbations, we are just running gradient descent. Right? Yeah. It's the same as the epsilon parameter in the second order stationary point that you want to find. Okay. So between 2 perturbation conditions, the only step that we are running is the step 4, which is just gradient descent, right? And what is the perturbation condition? So we check for 2 things. So one is that the norm of gradient f of xt is small, meaning that we might be at a saddle point. Okay. And the second one is that we have not added a perturbation in the last several iterations. Okay. So we'll make sure that once we add a perturbation, we will not add perturbation for the next so many number of iterations. And after that, we'll again check whether the norm of the gradient is still small, and then we'll add a perturbation. Otherwise, again, we don't add. Okay.
But this is small means like how do you?
So yeah, so this again can be is epsilon. So we are looking at epsilon second order stationary point convergence. So we'll check whether the norm of the gradient is smaller than epsilon, and we have not added any perturbation in the last several iterations. Again, several also has a quantitative meaning, but we check for both of these conditions, and then if both of them hold, then we add perturbation. Otherwise, we don't add perturbation. Okay. So let's quickly try to see how perturbation can help. So let's say my data point, my iterate is exactly at this saddle point, right? So when we do a perturbation, it moves slightly to a different place, right? And then we do gradient descent starting from that point. So it moves gradually because it has come off the saddle point. It has some gradient. It gradually moves away from in this negative direction, right? So intuitively, this is the phenomenon that we are trying to explain quantitatively in terms of how long does it take to escape and so on. Okay. Okay. So if we just consider the same saddle point that we have here, when we do this random perturbation, it can fall in a ball of radius r here, right? Out of that, we look at what are the points, and then we also saw that after that, we'll just be doing gradient descent for a certain number of iterations. So the question that we would like to ask is, if we look at the set S of points around the saddle point from where gradient descent does not escape quickly, right? Meaning in polylog of d iterations, we want to kind of bound the volume of that set. Because when we do this random perturbation, the probability that the ball will fall in this set is proportional to the volume of that set, right? If the volume of that set is small, then the probability that the iterate falls into that set is very small. And then with high probability, it will fall outside. And by definition, S complement is the set of points from where gradient descent escapes quickly, right? So the key technical question that we would like to answer is what is the volume of this bad set S? Okay. And if we are able to show that the volume of S is small, then we can that implies that perturbed gradient descent can escape saddle points efficiently. Okay. So let's look at some simple examples to understand how the set S looks like and what we can say about it. So if you just look at the two-dimensional quadratic case in which the function f is half x transpose this 1 0 0 minus 1 matrix times x. Okay. So the Hessian is just given by this matrix, and as we can see, it has one positive and one negative eigenvalue, and x equal to 0 is a saddle point because the gradient is equal to 0 there, and the Hessian also has a negative curvature direction, right? Now, if you look at any xt around the origin, x0 around the origin, and then see what gradient descent does, xt plus 1 is then given by this linear equation, which is 1 minus theta 0 0 1 plus theta times xt, right? So we see that the negative eigendirection here corresponds to a eigenvalue which is larger than 1 in the gradient descent operation, right? If we keep applying this repeatedly, if we do multiple steps of gradient descent, then this second coordinate will blow up whatever there was initially. Okay. So for so by definition, the set S is such that gradient descent starting from that point does not escape quickly, right? And here we see that whatever the second coordinate of x0 was, it will be blown up exponentially at 1 plus theta, which means that it will quickly get a very large negative value, right? So the function value will be very large negative because of this, right? So the only possibility for set S is that the second coordinate is actually very, very small. Okay. So in this context, we see that the bad set S is actually this thin strip around origin. Okay. Because the strip is very thin, the volume of the strip or the area of the strip is very small. So in this case, we can argue that like the volume of S is very small. Okay. Similarly, when we go to the three-dimensional quadratic case, where the Hessian is 1 0 0 0 1 0 0 minus 1, we again have one eigenvalue which is negative, and the origin is again a saddle point. And again, when we do gradient descent update, it actually is a linear operation with the third coordinate 1 plus theta actually blowing up. Okay. So in this case also, S turns out to be a thin disk because for this not to increase the third coordinate, the initial value of x0 has to be very, very small, right? So S is here a thin disk, and consequently the volume of S is again very small. Yeah. Yeah, so for quadratics, we have this very nice linear update rule that gradient descent gives rise to. And because of that, we are able to do this. So we'll come to, so the technical question is precisely what can we say when it's not quadratics like this, but it's like a general function, right? When the function is general and not a quadratic, then what can we say? It turns out that S can be shown to be a, like it could be deformed in whichever way, it will not be very nice. But what we can show is that it's actually very thin in one particular direction. And because it is thin in that direction, volume of S is going to be very small. So there are two key ingredients of the proof. So one is called improve or localize, and the second one is what is a coupling argument. So improve or localize is actually very similar to the things that we have done on the board this morning. So we recall like the same inequality that we did earlier today, which is f of xt plus 1 is less than or equal to f of xt minus theta over 2 times norm square of the gradient. Okay, this is just because of the smoothness of the function. Now we know that grad f of xt is nothing but xt minus xt plus 1 over eta. Okay, this is because of the gradient descent update rule. So if we rearrange this quantity, what we get is that norm of xt minus xt plus 1 square is less than or equal to 2 eta times f of xt minus f of xt plus 1. What this is saying is the amount of distance moved in any given iteration is less than or equal to the amount of function value decrease that we have seen in that iteration. So if we add all of them and then we use Cauchy-Schwarz, we can bound the distance moved by gradient descent in t steps. So x0 minus xt norm square is less than or equal to 2 eta t times f of x0 minus f of xt. So the right hand side is the amount of decrease that we have seen in the function value times the steps 2 eta is step size, t is the number of iterations, and the left hand side that we are getting bound on is the squared distance of that the gradient descent iterates have fully moved. Okay, so the upshot of all of this is that either the function value decreases significantly, like either this term has to be large, right? If this is not large, meaning that this is small, then it means that the iterates have not really moved much. So even the distance that the iterates have moved are small. Okay, so that's why we call this improve or localize, meaning that either the function value increases quite a bit, or we have been able to localize the dynamics of gradient descent to a very small region, right? And this will be useful later on. So we'll come to this. So the second part is what is called a coupling argument. So the idea is the following. So we look at 2 points u and w, which are separated by like a very, very small distance, which is square root of epsilon over d. Okay. And what we want to argue is that both u and w cannot lie in the bad set S. Okay. And what that would say then is that if you measure the thickness of the set along this particular direction, along this direction, then the thickness at any point is very small. It can be at most square root epsilon over d. Because if the thickness is larger, then you can find 2 different points which are separated by this kind of distance, and both of them cannot escape from the saddle point using gradient descent. But this argument, this lemma precisely says that that is not possible. Okay. So what this says is that if you take 2 points u and w, which are separated by a very small distance in this some special direction, then either gradient descent, so you consider gradient descent starting from u, and then you consider gradient descent starting from w, right? What this is saying is that gradient descent from at least one of these points has to quickly escape from the saddle point. Okay. So let me try to give more intuition on how we prove something like this. So if gradient descent from either u or w goes outside a small ball, it escapes, meaning that the function value decreases. This is because of improve or localize, because we are saying that if the function value has not decreased, then they have to be really localized in a small ball. But if both of them kind of goes outside, both of them go out, either of them goes outside a small ball, then that thing has to have decreased the function value by quite a bit. And if gradient descent from both u and w lie in a very small ball, then what we can do is that we can actually construct a very good local quadratic approximation for this function, right? And we can, for this quadratic approximation, we saw earlier that this bad set is exactly like this thin disk and has a very small volume. So we can exactly quantify this set as. And then once we show it for the exact quadratic, we can bound the approximation error between this quadratic approximation and the actual function within this small ball, because like this guarantees that we are only within the small ball. For that, we use the Hessian-Lipschitz property and the fact that we are only concentrating on iterates in a very small ball. Okay. So roughly, this is the intuition for why at least one of this u and w have to escape when we do gradient descent. Okay. Okay. So let's just putting everything together, we have this gradient descent step, and we saw that if the norm of the gradient is very large, the function value decreases just by using this argument. And if the norm of the gradient is small, then there are 2 possibilities. One is that we could be at a saddle point, or we could be at a second order stationary point. Okay. If we are at a second order stationary point, we are okay. But then we don't know whether we are at a second order stationary point or saddle point. So in both cases, we end up adding perturbation and then running gradient descent, right? And so if we are at a saddle point, we know that with high probability, this will decrease the function value. That's what we just showed. And if we are in this situation, again, there are 2 possibilities. Either we move away from the second order stationary point, in which case the improve or localize again tells us that the function value has decreased, right? Because the iterates have moved. If they have not moved, then it means that we are actually close to second order stationary point. So we'll still be at second order stationary point. Okay. So this is the overall idea of the convergence rate for second order stationary points for perturbed gradient descent. Any questions at this point?
So if you have parted once, why are you waiting for a very long time, reasonably long time for another perturbation?
Actually, there are two versions. So the proof here turns out to be much easier to do because between two perturbations, we are just analyzing gradient descent, right?
Yes.
So the proof is much simpler, but then we also have a different proof where you add perturbation every iteration.
Yes.
Even that one is fine, but the proof is a bit more complicated. Yeah, but the idea behind both of them is the same.
Okay.
Okay, so let's now move on to the main ideas behind the proof of accelerated gradient descent. So as we have discussed already, so perturbed gradient descent has this convergence rate of poly log d divided by epsilon square, and accelerated gradient descent can improve the dependence on epsilon from epsilon square to epsilon to 1.75. And I'll briefly describe the main ideas behind the proof of this accelerated gradient descent result. Okay, so let's recall Nesterov's accelerated gradient descent. This is actually written here in a slightly different form. Actually, the Vt here is also different from the Vt that we used earlier. Here, Vt actually refers to the velocity, but the form, like the update here, is exactly similar to what we saw earlier in the earlier lectures. So here we are looking at xt plus 1 is actually a gradient descent at a different point. We called it yt in the previous lecture. So yt is xt plus 1 minus theta times vt, and this xt plus 1 is precisely the gradient descent at yt. Okay, and vt here we call it velocity, is basically it's keeping track of the rough direction that my iterates are moving from. So initially my iterate was xt, now it's xt plus 1. So vt plus 1, the velocity is just looking at the direction from xt to xt plus 1. Okay.
Praneeth, I mean, sort of relate. I'm not directly related to, but I think at some point you mentioned that this is a bit different from just momentum.
Yeah, so I'll come to it. So this is just Nesterov's accelerated gradient, okay. But the precise algorithm that you analyze has maybe a couple of modifications. I'll come to that the next.
And this is somehow more efficient. Like this is faster than the momentum algorithm, is it?
No. So this is exactly the momentum algorithm.
This is the momentum, but no, I'm saying like if you just in terms of this underdamped dynamics,
yeah.
If you there's another more naive discretization.
So it's about discretization.
Yeah, the discretization is different, right? But the other discretization that is less, the convergence is slower. Is that right?
So I have only spoken about maybe one discretization so far,
right,
which is Nesterov's accelerated gradient. What we do is not maybe so much a different discretization in this work. We do the same discretization as Nesterov's accelerated gradient, but there is some issue that comes up with keeping track of the potential function with in the non-convex setting. But the different discretization is what is called Polyak's heavy ball method. That's still in the convex setting, so that's known to work for quadratic functions, but not for general convex functions. But I'm not going to talk about it today. Yeah. So this is all called Nesterov momentum, this kind of discretization. Yeah. So the challenge in in the convex function setting, if you recall, we were constructing this like different phi functions that we were using to keep track of both lower bounds and upper bounds, and we were doing something which is very specific for convex functions. And in particular, even though there are some potential function arguments, they all depend on optimum x star. And in the non-convex setting, there is no natural notion of an optimum x star because we are trying to converge we are converging to some stationary point. We don't even know which stationary point we are going to converge to, right? So the key challenge is in adapting known potential functions because they depend on the optimum x star, and optimum x star does not really make sense in the non-convex optimization setting. Okay, so in order to overcome this, if we go back and look at the small step size limit of Nesterov's accelerated gradient descent, so there is this differential equation view where we can think of accelerated gradient descent as actually a discretization of the ODE given by this. So this actually has a very simple physical interpretation, which is that if you look at x, if we consider x as the position of a particle, right? X double dot is just the acceleration, and then we have a coefficient of friction theta twiddle, and then x dot is the velocity. So this is the force due to friction which is flowing down the particle, and then we have this minus grad f of x, which is actually the force that's acting because of the potential energy of the particle that the particle is in. Okay. So again, if you multiply this entire equation by x dot and integrate from t1 to t2, then we get something which is again has a lot of physical meaning, which is f of x t2, which is the potential energy at time t2, plus half x dot t2 square, which is the kinetic energy at time t2. This is equal to the total energy at time t1 minus theta twiddle times this integral. So this entire thing is the amount of energy that's dissipated due to friction, right? So the key insight that this gives us is that we can actually think of this as the potential, as the energy function that the dynamics is actually minimizing in the limit, right? So earlier for gradient descent, for example, we were thinking of this kind of equation, f of xt plus 1 is f of xt minus this thing. So it monotonically is decreasing the function value itself, right? Here Nesterov's accelerated gradient, or like in the limit, this ODE is not minimizing, is not monotonically decreasing the function value. It's decreasing the function value, which is the potential energy, plus this kinetic energy, which is the total energy. Okay. So somehow we have to keep track of this entire total energy for getting a better handle on the accelerated dynamics. Okay. Okay. So yeah, so the punchline of this entire exercise is that this total Hamiltonian, total energy or the Hamiltonian, this thing decreases monotonically, at least in the small step size limit, in the differential equation limit of this method. But it turns out that when we discretize it, where we have iterate xt and then velocity is vt is equal to just xt minus 1, it turns out that this does not always hold, because there is only there are limits on how much step size you can use for discretization, under which this Hamiltonian decrease is still preserved. So more concretely, so the Hamiltonian, this is the total energy, decreases monotonically if f is not too non-convex between xt and xt plus vt. What we mean by too non-convex is that if we look at the function joining on the line joining xt and xt plus vt, then there is a large negative curvature at between the lines on the line joining xt and xt plus vt. So if that is not the case, if the function is not too non-convex, then the Hamiltonian decreases monotonically. And if it is actually too non-convex, meaning that there is a large negative curvature between xt and xt plus vt, it turns out that the discretization can actually increase the total, like the total Hamiltonian here. Okay. So this is the key challenge in going from the differential viewpoint to the discretized setting. And the one of the key insights here is that if the function is too non-convex, then we can just reset velocity to be equal to 0 or move in the non-convex direction. And this is what we call negative curvature exploitation. So I'll cover this in a bit more detail in the next couple of slides. But roughly speaking, if we just discretize using Nesterov's discretization, it works perfectly fine for convex functions, but it does not decrease this total energy for highly non-convex functions. In particular, we are saying the precise kind of non-convexity which breaks down this Hamiltonian decrease is the high negative curvature between xt and xt plus vt. So you look at the line joining these two things, and then in this one dimension, like it has a high negative curvature. Okay. And in order to deal with those kind of high negative curvature settings, we do something called negative curvature exploitation. Otherwise, we just use Nesterov's discretization from the convex setting. So any questions on this part? Okay, so let's look at how the argument might proceed. So if the function between xt and xt plus vt, so we'll just look at, so this just requires, because this is a function on a single line, right? We just need to compute the function value at either of the endpoints and then the gradients, and then we can identify whether the function has high negative curvature or not. Okay, because like, so if you look at convexity, it basically gives us a lower bound on the function at say xt plus vt, dependent on the function value at xt and then the gradient at xt, right? And we are seeing where this convexity condition is maximally violated. So that only requires gradient computations at xt and function value evaluations at xt as well as xt plus vt. Okay. So if it is not too non-convex, we just do the accelerated gradient descent step. And this is precisely the Nesterov discretization of the Newtonian dynamics. And in this case, we have already argued that the total Hamiltonian actually decreases. Okay. If it is too non-convex, then there are two situations. So one is the norm of Vt is large or the norm of Vt is small. If the norm of Vt is large, we just set it equal to 0. Okay. And then this naturally decreases because earlier Vt was something very large and now Vt is being set to 0. So this automatically decreases this quantity, and then we are again in this situation. Right? We go to the next iteration. So the other thing that we need to handle is when the norm of Vt is actually small. Okay. And in this case, it turns out that we can actually move in either plus or minus Vt direction. Note that norm of Vt is small. And so what we mean by that, xt plus 1 is xt plus or minus Vt, depending on which might be better. So we have to make a choice here, plus or minus. And what we want to argue is that there is at least one direction which can actually decrease the total Hamiltonian. And the reason for that is that between xt and xt plus Vt, we have a negative curvature, right? So we have something like this happening, right? So this represents negative curvature. And we look at the gradient and we see that at least one of the plus or minus Vt directions decreases f of xt, because we just look at which direction is more aligned with the negative gradient, and then we just move in that direction. And because of the high negative curvature here, it means that the norm of grad f of xt will decrease the function value quite a bit here. So because it decreases f of xt, we can then conclude that, and Vt is not changed, right? So we can conclude that the total Hamiltonian still decreases. Okay. So overall, what we have been arguing is that depending on whether the function is too non-convex or not between xt and xt plus Vt, we have two different analysis. And in this setting, where there is a lot of non-convexity, it turns out that the argument is easier in the sense that in a single step, there is a lot of decrease. Okay. So what I mean by a lot of decrease is that if you want to get a convergence rate of 1 over epsilon to the 1.75, we want to have at least on average some amount of reduction in function value in every step. And when we encounter this kind of situation, we have enough amount of decrease in single step. But here it turns out that that's not the case. And in a single step, there may not be enough amount of decrease. We have to do kind of an amortized analysis over multiple iterations. Okay. And here again, we use this improve or localize kind of idea, which is that because the total Hamiltonian decreases, and in particular quantitatively it decreases by this theta over 2 eta times norm of Vt square, where Vt is the velocity. So this is like the amount of energy dissipated due to friction, right? We can, and Vt was just equal to xt plus 1 minus xt, right? So we just take this onto the left hand side and we see that the total sum of squares of all the distances moved by the accelerated gradient descent algorithm is upper bounded by the function value decreases. Right? So now we can again have this improve or localize, meaning that either the function value decreases significantly or the total amount of movement that the iterates have made is very small, right? This then again helps us to approximate. So if the function value has not decreased significantly, right, it means that the iterates are all confined to a small region. And within this small region, we can again approximate the function locally by a quadratic function and then perform computations exactly for this quadratic. And then because we are guaranteed that the iterates are confined to the small ball, we can approximate the errors between these computations as opposed to what would happen for the full function using the Hessian-Lipschitz condition. And the precise computations again are somewhat technically challenging, but overall, like this is the main idea behind the result. Okay. So So this is all I wanted to say about non-convex optimization. I can take any questions, and then I want to switch gears into convex concave minimax optimization.
So can you go back to the previous slide? Right, yeah. So, so here, I mean, what is this direction plus minus? I mean, if you're doing in many dimensions, I mean, how do you choose this?
VT is already given direction, right?
What is the, like it's the...
So VT is the velocity. So it's one of the iterates that we are maintaining. So the algorithm.
Okay, in any direction, huh?
Yeah, that VT is equal to xt plus 1 minus xt.
Okay.
Or VT is xt minus 1.
No, like in higher dimension, like in one dimension, I can see that it will, okay, but in higher dimension also, it will always work. Is it? No, like, no.
Yeah, so it will always work because we are saying there is high non-convexity in this direction. Somehow, like in that iterate, you are just moving between xt and xt plus VT.
Okay.
Right? Meaning that your iterate has moved from xt to xt plus 1. Right?
Right. Yeah. No,
xt,
but like if it's a saddle point, supposing you moved in the wrong direction, and then minus will always bring you, will decrease the, like the small VT case, a small mod VT case.
Yeah.
Even like in 1D, I can see that the opposite direction will always decrease the energy function.
So I guess I'm saying that this basically boils down to a one-dimensional case at this point, because we are saying that it's highly so we are only looking at the line joining xt and xt plus VT.
Okay.
Right? We can just look at this one-dimensional objective. And what I'm saying is the function is highly non-convex in this one dimension, meaning that there is a high negative curvature. So there is at least one direction which significantly decreases your function value.
Okay. Okay.
The function can be in 2 dimensions, but what I'm saying is you're only concerned in this particular step, you're only concerned about the direction, like one dimension, which is joining xt and xt plus. I'm just saying like a straight line. Yeah, literally just the straight line that joins xt and xt plus VT. You look at, so you parameterize it by say some t, and then you draw the function as a function of t. So it's just a one-dimensional thing, and then you see whether it has negative curvature or not. If it does not have negative curvature, actually what we are saying is that so what we're saying is that this total Hamiltonian decreases, right? So you only have to care about non-convexity in that particular direction. Rest of the things may be non-convex, maybe not, but it doesn't matter for this purpose.
Just to be clear, I mean the Nesterov algorithm that you wrote here, it's is it the same that you wrote in the?
Yeah, it's the same. It's just different written differently, but they're equivalent.
Okay.
Okay, so maybe so I'll maybe use the blackboard now. I don't need the.
And Naveen, you can remove the screen.
Okay, so minimax optimization refers to problems of this form where we have a single objective f which depends on say two sets of variables x and y, and we would like to minimize in the x variable and we would like to maximize in the y variable. And there are several places where this comes up. One of the most popular ones is in game theory, where this is called zero sum. These are called zero sum games, two-player zero sum games, where x corresponds to. So there are two players. So one has a choice x to make, the other one has a choice y to make, and the payoff of the y user is given by f of x comma y, and the payoff of the x user is given by minus f of x comma y. Okay. So one is in game theory, where these are called two-player zero-sum games. And the second one, which is there are many more, but the second one I would like to mention is more optimization oriented, which is that if I want to solve a constrained optimization problem, min over x, f of x, subject to g of x less than or equal to 0, right? So if you write the Lagrangian version of this problem, it would turn out to be, so we first write say h of lambda, sorry, h of x is max over lambda greater than or equal to 0. Okay. So if we define this function h in this particular way, what we can say is that h of x is equal to f of x if g of x is less than or equal to 0, and this is equal to infinity if g of x is greater than 0. Okay. Okay, so the original objective is to solve this constrained optimization problem. So we want to minimize f of x subject to a particular constraint on x, right? And when we write the Lagrangian formulation, so we first write this h of x, which is max over lambda greater than or equal to 0 of f of x plus lambda g of x, and we can this follows easily that h of x is equal to f of x if g of x is less than or equal to 0, because the maximizer is going to be just lambda equal to 0. Okay, and h of x is going to be equal to infinity if g of x is greater than 0, because then lambda can be taken all the way to infinity. Right? So this constrained optimization problem is equivalent to minimizing h of x, which is unconstrained. Right? So if we just put in the definition of h of x from here, what we get is actually a minimax optimization problem. Okay. So it turns out that these minimax optimization problems are much more challenging than standard optimization problem, as you can imagine, because it seems, even to think about it, seems a bit more complicated. But there is one widely studied setting where it's known how to, this has been very widely studied, and that one is what is called convex concave setting. So Let me see. So f of x comma y is said to be so I also have not defined concave.
So, Praneeth, so then this looks like a saddle point.
This is a saddle point problem. Yeah. So convex concave minimax optimization or saddle point. So the reason I said minimax optimization is in general, if I don't tell you something about the function being convex, concave, and so on, it does not necessarily have to have this saddle point. So saddle point actually makes sense when f is convex in x and concave in y, which is what I'll be maybe talking about today. But in general, these days people also are interested in understanding non-convex but concave, or non-convex and non-concave minimax optimization and so on. There, it's a bit more subtle and is not the same as saddle point optimization. Okay, so concave just means that minus f is convex. Okay. So in general, there is no what is known as weak duality always holds. So this does not require convex concavity. So if you see here, we have an order here. So what this means is that you first fix an x. You for a fixed x, we compute like the max over y, and then we'll get this resulting function which is like this h, and then we minimize over x. So there is an order between min and max. So what weak duality says is that there is an inequality between the two orders. Okay. So this is always true. There is no assumption that we are making here. This is always true, and the reason is the following. So let's say we fix some x twiddle and y twiddle. Okay, we know that min over x, f of x comma y twiddle is less than or equal to f of x twiddle y twiddle, which is less than or equal to max over y x twiddle comma y. Right, and this is true for every x twiddle and y twiddle. So we can take a max over y twiddle here. So now we just remove this quantity and then have this inequality. Right. So weak duality always holds. There is no assumption that we made here. But the famous Minimax theorem due to initially by von Neumann and then Sions says the following. if F is convex concave, and X and Y are compact, then this is actually inequality. So what we'll do now is actually a constructive version of constructive proof of this statement, which also tells us how to actually find. Okay, so the solution to this is called Nash equilibrium, and I'll just write down what it means. But what we'll now do is to show that a natural algorithm, which is called gradient descent ascent, can actually find this Nash equilibrium, and in the process also proves, like, gives a constructive proof of Sion's minimax theorem for convex concave functions. Okay. Okay, so we say that X hat, yeah, so X hat Y hat is an epsilon approximate primal dual pair if okay. So the weak duality basically says that for any X hat Y hat, this thing is smaller than or equal to this thing, right? Because this is less than or equal to f of X hat Y hat, which in turn is less than or equal to this quantity, right? What primal dual pair means is that we are given a point X hat Y hat such that this and this are actually not very far away and are at most epsilon far away. Any question?
Could you explain this before the theorem? Inequality that you wrote down before the theorem.
Yeah, maybe the mic.
Could you explain this inequality that you wrote down before the theorem? How does that derive from the first one?
This one?
Yeah.
So, so just ignore this and then just consider this and this, right? So this is true for every X twiddle, Y twiddle, right? It means that if I take a max over Y twiddle here, that should still be smaller than or equal to this because it's true for every Y twiddle, right? And similarly, now I get a max here. Similarly, this thing is actually less than or equal to this for every X twiddle. So in particular, it has to be less than or equal to the smallest value this can take over X twiddle. So that's why I can put a min here. So, like if you notice, this is precisely saying the opposite thing of the weak duality, right? And we always have some slack here, and this is the quantification of how approximately we are satisfying the converse of that. Okay, and just by looking at min over x and max over y, the natural algorithm that we can think of is this gradient descent ascent. Okay. And it just does gradient descent in the minimizing variable. So is the algorithm clear? So the algorithm is very simple. So we have a minimizing variable, so we do gradient descent, and then we have a maximizing variable where we do gradient ascent. Yeah, so there are actually multiple variants, but this is what is called gradient descent ascent in general. This will, yeah, so same iterates. So this is called, I guess, simultaneous gradient descent ascent. There are maybe sequential gradient descent ascent, and yeah, there are also other variants and so on. Yeah. Yeah.
This inequality that you wrote down here, this is in general true, is it?
This is always true, right? I have not made any assumptions here.
And what does this theorem imply then?
This says that this less than or equal to is actually inequality.
Okay, and this is true when the x and y are compact.
XY compact and F is convex concave. This is an important assumption.
Okay, and this assumption was not there.
This was not required in this. This is generally true for any F. Yeah.
Could you sort of tell me the definition of compactness here?
Compact is just that, at least in real spaces, you can think of as bounded and closed. So any bounded set which is closed, not open. So for example, you can think of like X being some L2 ball or simplex. All of these are compact sets. Okay, so for minimax optimization, at least in the convex concave setting, this is the notion of optimality, which basically tells us that x hat y hat is an appropriate, like approximate primal dual pair, meaning that there is not much gap between the, this is called the primal value and this is called the dual value, right? And simultaneous GDA is a natural algorithm that we can think of for trying to solve these minimax optimization problems, right? So in the rest of this lecture, I'll just like state and prove a theorem which gives us, which tells us that gradient descent ascent can actually find approximate primal dual pairs for convex concave minimax optimization, and we'll see what exactly the rate is. And as I mentioned, like this also acts as a constructive proof of Sion's minimax theorem.
Praneeth,
yeah,
one quick comment. Another application that you didn't mention, perhaps you mentioned the game theory side. But in statistical decision theory, there is this minimax estimators.
Yes, yes.
That's a corresponding statistical thing.
Right.
That also uses this minimax optimization.
Right. And I mean, particularly if you think of lower bounds, either statistical, computational, any of these minimax theorems are quite useful. So there is Yavo's minimax principle in computational complexity, and similarly in statistics, there are lower bounds. I mean, the minimax estimators is one kind of optimality that you would want to prove about statistical estimators. Yeah.
Right.
So the theorem that I want to prove is the following. So if F is convex concave, and G Lipschitz. Okay, so in here G Lipschitz means okay. Then GDA, average iterates. After T iterations. So X bar T is nothing but 1 over T. Satisfy this epsilon approximate primal dual property in the following sense. Okay. So this is the important term, which says that X bar T, Y bar T is a approximate primal dual pair, epsilon approximate primal dual pair, where epsilon can be bounded by this 2gr over square root T. Okay. So as T goes to infinity, this goes to 0, and this gives us the precise quantitative rate of convergence of gradient descent ascent in terms of finding these saddle points. So actually, given that we have done the proof of gradient descent, this also follows along very similar lines. And the idea is the following. So we have xt plus 1 minus x star square, or like there is no x star here. So let's just consider any x. Similarly, for yt plus 1 minus y, we have a plus here because we are doing gradient ascent. So if we let delta t to be xt minus x square, what we have is that delta t plus 1 okay. So if you use the convexity in terms of the x variable for a fixed yt, what we get is the following. So f of x comma yt is greater than or equal to f of xt yt plus okay, this is by definition of convex, like just by the assumption that f is convex in the x variable when we fix any particular yt. So we fix yt here, and just in terms of the x variable, it's convex. And similarly for the y variable, it's concave, which means that xty is less than or equal to okay. So fixing xt, f is concave in the y variable. So the function value at xt comma y is upper bounded by the first order Taylor expansion at xt yt, right? So if we get bounds on this term and this term and use them to bound both of these, right? So that's what we will do. Okay, so what we get is delta t plus 1 is less than or equal to delta t minus 2 eta. So we have this term grad f of xt yt with x minus xt that appears here, and grad y f of xt yt y minus yt that appears here. So we used the inequalities that we get from here, and we just plug them into here. And the key part is that these things just cancel f of x t y t, and what we get is a bound on f of x t y right? And then we can take a telescopic sum and then average. So if we take a average here, what we get is 1 over t So this one, we are just taking an average, that's this one. This term, we're taking an average, that's this term. And when we take an average of this, all the terms cancel except for delta 0. So that's this one. And we have a 1 over t that comes up here. So that's this. And this one, when we take an average, we just get eta g squared. So by convex t, what we also know is that f of x bar t for any y is less than or equal to 1 over t and similarly f of x comma y bar t is greater than or equal to 1 over t. So just combining these two inequalities with this, what we get is f of x bar t comma y so delta 0 so this is less than or equal to r square eta t plus eta t square. So this is true for every x and y. We have not made any assumption about x and y here. So in particular, this will be true for when we take a max over y and then a min over x. So if we choose eta equal to r over g square root t, the right hand side is equal to 2gr divided by square. Yeah. Yeah, the step sizes have to be the same. That's great. So, like another way to think about this. So actually, you should we can maybe think about this as a joint gradient descent, where you think of this entire thing as a single gradient field, right? If you don't take the same step size, even in a single gradient, if you choose different step sizes for different coordinates, I guess like there you are still doing descent according to a different metric. So here, will that be true? Yeah, so that's a good point. I had never thought about it, but yeah, so in standard gradient descent, for example, you can take maybe one step size for one coordinate, another step size for another coordinate. It's just that you are doing gradient descent in a different metric. Here, I'm not sure if that viewpoint is there. I think it should be there. So maybe I need to work out, but at least from this proof, it's not clear. Yeah, so maybe I can stop here. I can answer any questions.
I mean, so this is kind of a again physics question.
Yeah.
I'm just thinking of like, let's say I have a potential defined on a torus.
Yeah.
And so this potential has, let's say, some saddle point somewhere.
Yeah.
Okay. And now and so I know the directions on the saddle point. Now, if I start from an arbitrary point, and so it looks like I can define the friction to be plus and minus in some directions.
Yeah.
And then it should converge to this saddle point. Is that right?
So, yeah, I mean, this is all for convex concave fitting, meaning that it has to be convex in the in one direction, like globally. So we are making this global assumption.
So it has to be globally, like in one direction, it has to be like that, and one direction.
Yeah.
No, but it has to be on a compact. Yeah.
On a compact.
On a compact. Yeah. So it can't be x square minus y square. No, it has to be on a right? Like on a period torus or something.
Compact. Actually, so you also need a compact convex set. I should mention that. So the reason is that eventually you're outputting some average iterate, right? So you're outputting some average iterate. So for this average to be, this is a condition that you have, like your average should be contained in the set. So this will be true only for convex sets. Yeah, that's also, yeah, even Sam's minimax theorem, the sets have to be convex compact. So if I define something on the torus, it's not a convex set. I guess, like, is there a parameterization that will make it convex? And then you have to work in that parameterization. I mean, at least if I look at it in the three-dimensional space, it's not convex. Is there like some other space to embed this where it will be a convex set? But the function, sorry? Okay. Some function on that. So I was thinking of like torus, like. But I can also think of it as like a 2D thing with surfaces periodic boundary. Okay. Okay. Surfaces are the same. Right. The boundaries are like so it's basically periodic in both directions. And have some function. Okay. Okay, yeah. Then for such a function, looks like what your algorithm does is like start from any point. So if I'm thinking of small iter, then it looks like a Madhava equation, not Madhava overdamped equation with a positive and a negative. And it looks like starting from any point, go to the saddle point. Yeah, actually, this is not so. this does not go to a saddle point. So we have only shown that like the average iterate has a saddle point property. So in particular, it could be something like this. So your saddle point is here and your iterates could be doing something like this, but their average will be the saddle point. It need not go right there. And yeah, so like at least for gradient descent ascent, like this averaging is crucial in Minimax. So earlier in the pure optimization setting, I mentioned that there are results which can also give you same guarantees for the last iterate. But for Minimax optimization, that's not the case. At least for gradient descent ascent, it's known that it will not converge. Only these averages are really the quantities that converge.
So for this, can we also, so you basically showed this accelerated version. of
Yeah,
the
so
gradient
there is no acceleration as such, but it turns out that, so gradient descent for Lipschitz functions got 1 over square root t. For smooth functions, meaning like the gradients are Lipschitz, we got 1 over t in the standard minimization setting. But here it turns out that gradient descent ascent itself, even if I tell you that the function is, if the function is smooth, we don't get anything better than 1 over square root t for gradient descent ascent. But there is something which is called a proximal algorithm, which can actually get a 1 over t convergence rate for smooth functions. And that in some sense is equivalent to acceleration in the standard setting.
So it's not as easy as like the one that you showed for when we were doing this gradient descent case. You just basically added this VT term there, right?
This is actually, I would say, even simpler than acceleration. Acceleration, at least, there was some algebraic things that we had to do to understand like what's the largest alpha t to pick and so on. Maybe not that much of intuition why we are getting 1 over t square and so on. But a proximal algorithm is actually very simple to describe. But for smooth functions, it turns out that it's also possible to implement. So the idea is that you want to find xt plus 1, yt plus 1, where it does not satisfy this condition, but rather it satisfies this condition.
Is it t plus 1?
T plus 1 everywhere. So this is an implicit equation. So if this was xt, given xt, I can explicitly compute what xt plus 1 is. But if I want this to be satisfied for xt plus 1 by yt plus 1, this is actually an implicit condition, right? But it turns out that for smooth functions, this can be efficiently found. And the algorithm is also very popular. So they're called extra gradient methods. So actually, let me combine both of these as the following. So z twiddle t plus 1 is some x twiddle t plus 1 . Okay. Now the actual next iterate zt plus 1 is given by the following. So the extra gradient method basically says that from the current point, you take a gradient descent ascent step, right? You go to this new point x twiddle, y twiddle. Now you compute the gradient at that point and then use that direction to update from x, dy. So this is different from taking 2 steps of gradient descent ascent. So you're keeping the same value, but instead of using the gradient at this point, you're first taking a gradient step and using the gradient at that point to update from the current point. Okay. So what we can say about this is that if f is L smooth and convex concave, then for this algorithm, we get L R square over T convergence rate. Okay. But gradient descent ascent itself cannot get anything better than square root T, even if I guarantee you that the function is L smooth. So this kind of extra gradient, so it's called extra gradient because you're taking gradient, like 2 gradients for every step.
So this one, how do you compute the
this one?
Okay, so you're first doing
you first compute this
first
point,
iterate this one,
and then you compute the gradient here, and use this gradient to update from x, dy.
Okay. So it's some kind of like Stochastic. It's some kind of like a midpoint gradient, is it? Like a
Not midpoint. You can think of it like that,
like
maybe.
Some
yeah. So this is like an implicit equation.
Okay.
Right. Yeah. So maybe if you think of Euler discretization of this dynamics, this is like the forward discretization.
Yeah.
And gradient descent ascent, like the implementable standard implementable version, is the backward discretization. Okay. It turns out that again doing the right discretization is important, and this is one way of kind of approximately solving this using only like one extra computation. Like roughly, otherwise, like another thing you could do is you keep repeating this process, right? Mm-hmm. So you do this, and then you use this gradient. You'll go to some x twiddle, x double twiddle t plus 1, y double twiddle t plus 1. Use that gradient, and then you update using x to y. You get x 3 twiddle and so on.
So this looks like some kind of this Stochastic this thing like for stochastic calculus, right?
I don't know what.
No, like instead of doing at the beginning, like calculating the force at the beginning, you calculate somewhere in the midpoint, basically.
Yeah, I mean,
right?
The ideal thing is if you can actually do this, this is the best. If you can do it at the other endpoint, like the forward Euler discretization, that's the best. But that's an implicit equation. We don't know how to do that. So this is an approximate way of trying to get there.
Okay. Yeah, yeah. And why is that one is better than actually taking the gradient at the point before?
Yeah,
you're saying that that one is better than
algebraically. What happens is that you get this additional terms which you are paying for, right? We have these g square kind of terms. So if this was not gradient at xt yt, but rather this was gradient at xt plus 1 yt plus 1, you'll actually not have this term. Uh-huh. So even if you look at like why we are getting the square root t rate, there were 2 terms, right? Uh-huh. And there was this other term which we have to balance. Okay. Right? If we did not have this term, then we are getting a 1 over t rate. Okay. Right? We can choose eta to be some constant if we did not have this term. Okay. And the reason we have this term is because we are using gradient at the current point. But if you use gradient at xt plus 1, then actually this term will no longer be there. Algebraically, that's yeah. 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 Yeah, yeah, yeah. That's another way to look at it. Yeah. Yeah.
So we have the diameter term coming in here.
Yeah.
Now, if I start off this process at a point which is close to an epsilon approximate primal dual pair, there is no guarantee.
Seems like there is.
You might still be taken to a far away.
Yeah.
So a bound where that epsilon is.
Unless you enforce it. So actually, one thing I was not very careful about is that because we are working in constrained like balls with diameters and so on. This is not just this, but we have a projection operator acting on top of this, on top of both of these, meaning that this is actually has to be a projection onto X to ensure that my iterates always lie in the constraint set.
Go as far as you can, staying in the set.
Staying in the set, yeah. And unless you enforce what you know that the starting point is indeed close to the optimum, maybe unless you enforce that in the set and then do the projections also within that set, I don't think we can get a dependence on the smaller quantity.
Maybe we break for lunch. And
Sounds.
so, yeah, thanks.
Thank you.
So, yeah.